You know, we're surrounded by one of the most incredible materials on Earth, but we probably don't give it a second thought. Today, we're going to pull back the curtain on the secret life of aluminum, exploring the amazing science that takes it from just a piece of rock to the very backbone of our modern world.
All right, let me ask you something. What do you think connects the phone in your pocket, the car in your driveway, and the plane that flies you across the country? I mean, they couldn't be more different, right? But believe it or not, they all share one fundamental, kind of hidden, building block.
And yeah, the answer is aluminum. This stuff is just everywhere. It's super versatile, it's light, it's strong. But the real question is, how does it get from being a raw ore stuck in the ground to being part of the high-tech gadgets we use every single day? So our journey has to start right at the source. And you've got to understand, creating aluminum from scratch is this raw, incredibly power-hungry process. It's a transformation that is, and I mean this literally, forged in electricity.
Okay, so at the very heart of all aluminum production is this one core scientific idea: electrolysis. Basically, what you're doing is blasting a massive electric current through the raw material to kick off a chemical reaction. This jolt of power is what's needed to literally rip the aluminum atoms away from the oxygen they're bonded to in the ore. Now, to make this whole thing work, you need two key players inside what's called a cell. You have the positive anode and the negative cathode. It's kind of like thinking of them as the plus and minus terminals on a giant battery. The electric current flows from the anode over to the cathode, and it's along that journey that all the magic happens. But here's the catch. That raw aluminum ore has a crazy high melting point. Trying to melt it directly would take an insane amount of energy. So, they use a special mineral, cryolite. This is the real secret ingredient. It acts like a super solvent, dissolving the ore so that the electric current can flow through it and do its job.
So, let's walk through it. First, you dissolve the raw ore in that cryolite all inside a big container they call a pot. Then, bam, you hit it with that massive electric current. As that current flows through, it separates out the pure aluminum, which is heavier, so it sinks down and collects at the cathode at the bottom. And from there, the pure molten metal gets siphoned off and it's headed for the furnace.
And when we say furnace, we are talking about some serious heat. We're talking temperatures over 1,000 degrees Celsius. This incredible heat keeps the aluminum in a liquid state, which is crucial for purifying it and getting it ready for casting.
Now, let's just zoom out for a second. That single pot we talked about, it's just one tiny part of a much, much bigger operation. A modern aluminum smelter is just a massive industrial plant with hundreds and hundreds of these pots, all connected together in a long line called a potline, all working 24/7 to make the metal that literally builds our world.
Okay, so that's how we get our hands on pure aluminum. But here's the thing. Pure aluminum on its own isn't actually that strong. The real wizardry happens next, when scientists and engineers take this basic metal and start designing it into a high-performance supermetal.
And to really get that, we have to go from the enormous scale of a smelter all the way down to a level that's completely invisible. Because a metal's true strength, its real character, it isn't something you can see on the surface. It's hidden deep, deep inside.
What we're talking about is its microstructure. Yeah, if you could zoom in 1,000,000 times, you'd see that all metals are made up of these tiny little individual crystals. We call them grains. And the size, the shape, how they're all arranged, that pattern determines everything about the metal. How strong it is, how bendy it is, everything.
So how do engineers actually control this internal architecture? Well, the main trick up their sleeve is called alloying. It's the art of mixing really small, precise amounts of other elements into the pure aluminum. You add a little bit of copper, for example, and suddenly you have an alloy strong enough for an airplane wing. Add some magnesium instead, and you get something perfect for a soda can. It's all about creating brand new materials designed for a specific job.
And this gets to a really fundamental trade-off in material science. When you're making an alloy, you can give it incredible tensile strength. That's its resistance to being pulled apart. But there's a catch. Often, the stronger you make it, the less ductility it has. It's more likely to just snap instead of bend. So for engineers, it's always this delicate dance, trying to find that perfect sweet spot between the two.
And that brings us to this critical number for any engineer: yield strength. Think of it as the point of no return. It's the absolute maximum amount of stress a material can handle before it bends and stays bent. This single number tells you how much weight a bridge can hold or how a car frame is going to crumple in an accident. It's absolutely crucial for safety.
But you know, a single big impact isn't the only thing that can break a material. What happens when it's stressed just a little bit, but over and over and over again? Just think about an airplane wing, flexing up and down on every single flight for years.
This silent killer is called fatigue. It's the slow, invisible buildup of damage from all those repeated cycles of stress. Tiny, microscopic cracks can start to form and grow until one day, almost out of nowhere, the part fails, even though it was under a load way below its original strength. So yeah, understanding and designing to prevent fatigue is one of the most important jobs in all of engineering.
So all of this naturally brings us to the future. We've seen how aluminum gets made and how it's engineered to be strong, but where is it all heading? Let's take a look at the big challenges and the cool innovations that are shaping the next generation of this amazing material.
As we saw, that whole electrolysis process uses a ton of energy, and that of course means it has a pretty high carbon footprint. At the very same time, our demand for even higher performance, lighter, stronger materials just keeps going up. So these are the big hurdles the whole industry is focused on clearing right now.
And the response to these challenges? It's pretty clear. It isn't about using less aluminum. It's about making it smarter, making it more efficiently, and making it perform even better. The answer, plain and simple, lies in innovation and new technology.
So what does that strategy actually look like? Well, it's kind of like a multi-front attack. First, you have scientists working on totally new smelting technologies that produce little to no carbon. At the same time, others are going back to the fundamentals, trying to improve electrical conductivity to make the whole process way more efficient. And of course, the hunt is always on for revolutionary new alloys that are stronger and more fatigue-resistant than anything we have today. You know, it reminds me of that old saying, the Stone Age didn't end because we ran out of stones. Progress isn't just about coming up with new ideas, it's about creating the new physical stuff that actually makes those ideas a reality. A new material can completely redefine what's possible for humanity. And that leaves us with one last thing to think about. Aluminum, without a doubt, was a defining material of the 20th century. It gave us modern airplanes, it gave us skyscrapers, it connected the globe. The big question is, looking forward, will a smarter, stronger, more sustainable version of aluminum continue to lead the way? Or is there an entirely new material out there, waiting to be discovered, that will completely reshape the next 100 years?